Hello everyone, we are going to show the proof for the triangle angle sum theorem, which tells us that in a Euclidean space, the sum of the measurements of the interior angles of a triangle is 180 degrees. Notice the claim that we are still on the Euclidean space. In short, this still covers the Euclidean geometry, or what we know as well as plane geometry. In that sense, we need to show that for any triangle under Euclidean space, the sum of the measurements of its interior angles is 180 degrees. We need to show it by using this given figure here. I have here triangle ABC with interior angles A, B, and C. With this, we need to show that the measurement of angle A, which corresponds to the red colored angle here, plus the measurement of angle B, which corresponds to the green colored interior angle here, and the measurement of angle C for the interior angle blue colored angle here, if we're going to sum them up, they must be equal to 180 degrees as claimed by this theorem. To show up for the proof, we need to use the two-column proof here where we list down all statements and corresponding reasons. Again, we need to make sure that the statements and reasons are arranged logically so that we could reach this intended target with a logical proof. In this case, for the first statement, we need to write what was given here. So 1, I'm going to write it here, triangle ABC with interior angles. Since they are all interior angles and they are angles, let me just use the symbol so that we could reach this later. So we have angle A, angle B, and angle C. And the corresponding reason for this is that this is what was given. Now that we have established the given, we need to come up with a situation here that is either connected to this or will connect to the next important statements that will help us yield this proof. Here, I'm going to add another figure here by construction in such a way that it will help me look into the relationships among these three angles here. Let us consider constructing line segment MN passing through vertex A here. In short, we're going to construct a line segment MN passing through this vertex, again vertex A, that is parallel to side BC. Okay? Again, I'm going to construct a line segment MN passing through vertex A that is parallel to side BC. In short, I'm going to draw a line segment covering the vertex A that is also parallel to side BC. You know already what parallel means, so it would look like this. I'm going to use notations, points here for M and N. So this is a line segment MN, which is parallel to side BC as claimed here by construction, and it passes through this vertex here. So again, I did that by construction. The reason why I made use of this process is for me to understand so that I could establish relationship among the interior angles here using this parallel line here. Looking into that, once you have constructed this line segment MN, which is parallel to line segment BC, let's use a notation, by the way. This could be the notation for parallel. Okay, like that. So I'm making sure that they are parallel in figure wise. After doing this, notice that I have made two additional angles here. I have here angle BAM or MAB if you want to, as well as angle CAN or NAC. This angle here as mentioned, and this angle here as well. So this is still part of the construction. I'm going to have here a statement here. So we have here additional statement making angle BAM, or again MAB if you want to, and angle CAN or NAC if you want to. Again, this is still part of the construction because this is a consequence of what I did when I constructed the said line segment with all of these conditions earlier. So out from this, I'm going to come up with this next statement which will relate any of these two to any of the additional two angles there at the bottom. But first, let's consider the relationship between these three angles formed here. I'm talking about the original angle A, but since we cannot use the angle A as a standalone angle since that vertex is shared by the three angles now, it is actually better to be called angle BAC or CAB. I'm going to look at the relationship of that to the newly constructed angles. Notice that these three angles here are adjacent angles. Aside from that, if we are going to add the measurements of these three angles here, they make up a straight angle. I'm talking about if I'm going to add this angle here, and this angle here, and this angle there, it makes up a straight angle here. This was made possible by the understanding that the given line segment AMN is a straight line segment under the Euclidean space. And all of these angles now can be summed up into a straight angle. So I could look into here and state that angle BAM, angle, this angle here, I'm going to call it BAC, and angle CAN makes a straight angle. The reason here could be the definition. Straight angle. In that case, I could make a connection wherein if I'm going to use measurements of angle BAM plus the measurement of angle BAC plus the measurement of angle CAN be equal to 180 degrees. Here, still straight angle, or you could also use the concern angle addition postulate. From here, notice that we have already established a relationship that will yield to 180 degrees, almost similar to our goal here. But this is not yet what our goal is. We need to show that the measurement of angle A plus the measurement of angle B and measurement of angle C is 180 degrees, and it's nowhere near to this yet. I'm talking about looking into the relationships within the measurement of angle BAM, this angle here, and any of the two, as well as the measurement of angle CAN to any of the two angles here. Notice that we have claimed that the line segment MN is parallel to side BC. In this sense, we could establish a rule that is related to the transversal cutting parallel lines. Let me try to extend this a little bit, just for imaginary lines. If we're going to consider this as an imaginary line extension, and this side BC, which contains this, is parallel to the line segment MN here, we could actually give that this side AB, if extended, is considered a transversal line cutting the two parallel lines. Same as true with this side here. If we are to extend, the line segment AC or side AC is a transversal line segment of the given parallel lines. This original side here and the constructed line segment at the top. My point of sharing you this one is that we could come up with the measurement of this angle here and that. But first, let us declare the type of angle pair it exhibits. If this is the transversal line cutting parallel lines, the type of angle pair exhibited by angle BAM and angle B here is actually the pair of alternate interior angles. So I could say here that angle BAM and angle B are alternate interior angles. The same can be made true as well with angle CAN here and the angle C, since they may be considered as alternate interior angles when we consider extension of side AC as a transversal line cutting the same parallel lines here. Notice, like this and that. So we could also write it here. Let's move it a little bit higher. We have angle CAN, CAN, and angle C are alternate interior angles. This is under the definition of a pair of alternate interior angles. Why is it that it's important for us to come up with a pair of alternate interior angles here as well as here? Notice that we have a claim that the line segment MN and the side BC are parallel to one another, and we do have a good relationship to alternate interior angles if those were made by a transversal line cutting parallel lines. I'm talking about their measurements. In this case, we have here 6. The angle BAM is now congruent to angle B, as well as angle CAN be congruent to angle C. This is by alternate interior angles theorem. Okay? Since they are now considered to be congruent, what we can say about their measurement is that the measurement of angle BAM is now equal to the measurement of angle B. Also, the measurement of angle CAN be also equal to the measurement of angle C. This is by definition of congruent angles. Okay? So we are now here. We have established a fact where it does include measurement of angle B and measurement of angle C, which is closer to what we are intending to. But we haven't found out angle A yet. So let me try to extend it here since our proof needs more statements and reasons. Let us consider here S for statement, and this is for R for reason, and I have here statement number 8. Where could we locate measurement of angle A now so that we could establish all of the relationships later? Our statement number 8 should include measurement of angle A, since we already established measurement of angle B and measurement of angle C, parts of our intended target here. But where should we locate measurement of angle A? Looking back to the figure, this is angle A as given earlier. However, since we have constructed a line segment MN, that vertex now is shared by 3 different angles. Thus, we can no longer call it angle A. However, earlier, looking back at statement number 4, BAC, instead of calling it angle A, we either called it angle BAC or CAB. Statement number 4 calls it angle BAC, and what we could actually say that they are just the same. They are just the same. We could state here that angle BAC or CAB if you want, this angle here in statement number 3 and number 4 is actually congruent to the original angle A. Again, this is talking about original angle A. This is by reflexive property. Okay, since they are just the same. And number 9 could tell us that the measurement of angle BAC is just the same as the measurement of angle A, the original one. Please not forget about this. And the reason for that is, again, definition of congruent angles. Now that we have reached this statement now, and we do have the statements earlier showing measurement of angle B and angle C, we are now ready to look into this perspective. However, from statements 1 to 9, there's only one statement that includes 180 degrees, and that's statement number 4, which tells us that the measurement of angle BAM plus the measurement of angle BAC plus the measurement of angle CAN is equal to 180 degrees out from the first 3 statements and corresponding reasons. Still, we are closer to this since we have statement number 7 and 9 that can help us connect statement number 4 to this statement number 10. Measurement of angle BAM originally is now the measurement of angle B according to statement number 7. Hence, I'm going to copy it here to this one. The measurement of angle BAM is now measurement of angle B. Okay, again, measurement of angle BAM is equal to the measurement of angle B. Then, measurement of angle BAC is actually the measurement of angle A plus the measurement of angle A plus statement number 4, the last angle, is the measurement of angle CAN, which is actually now given to us as angle C. Measurement of angle C be equal to, just simply copy, 180 degrees. This is done by substituting the angles which are the same in respect to their measurements. So by substitution property. If you would like to add here something, you can just simply rearrange it in such a way that it could look into that if you want to, but let's just make it into like that. Let's just rearrange it here. The measurement of angle A plus the measurement of angle B plus the measurement of angle C be equal to 180 degrees. And the reason that would correspond to just simply arranging this one is by commutative property. Okay, let me move it a little bit here so you could see. Okay, like this one. Now that we have reached this, we have proven the statement here already, and that will tell us that in any triangle in the Euclidean space, the sum of the interior angles is equal to 180 degrees. This is the proof for this theorem. It may seem too long, but this theorem is very important as we move further to other theorems which talk about sum of interior angles and the like. This is the proof for the triangle angle sum theorem, which tells us that in a Euclidean space, the sum of the measurements of the interior angles of a triangle is 180 degrees.